Good afternoon, everybody. Thanks for joining today's session of NCCAV seminar series. The past seminars and the plan for the future seminars are already available. If you don't have you did not have the chance to attend the previous seminars, they are all uploaded to the website, and you can go ahead and watch them online later. I would like to thank this opportunity to thank the sponsor, NC Duty, as well as other sponsors of the project Downtown Greensboro, Verizon, and RTI. With that, for today's meeting, it is our pleasure to have Dr. Wei Fan as the speaker. The title of the talk is Mitigating Freeway Congestion at Bottleneck Through Variable Speed Limit Control in Connected Autonomous Vehicle Environment. Dr. Wei Fan currently serves as a food professor in the Department of Civil and Environmental Engineering at the University of North Carolina, Charlotte, UNCC. He is the director of the US DOT University Transportation Center for Advanced Mobility Solutions and Education. Dr. Fan holds a PhD in civil engineering transportation from the University of Texas at Austin. He was a senior analytical optimization software development for the R&D development at SAS Institute in Cary from June 2004 until August 2006. And also, Dr. Wei Fang is the lead for Trust 2 of NCCAV Center. And with that, I would like to invite Dr. Wei Fang to get for today's talk. Thank you.
So, good afternoon, everyone. It's great to be with you, and I'm going to make a presentation entitled Mitigating Freeway Congestion at Bottlenecks Through Variable Speed Limit Control in Connected Autonomous Vehicle Environment. So this is one of the research we conducted for U.S. Department of Transportation, CAMSI UTC, about 2 or 3 years back. So obviously, there's we spent quite some time, about 2 or 3 years, on this study. There are a lot of research we may not be able to share with you, a lot of results. So about a half of them you're going to see today. Okay. So here is the overview of my presentation. Still loading. Ali, can you see this? It's advanced to the next slide.
You do see the slides. It is still on slide 1, on the cover slide.
Okay. So I probably need to close one of them. Close it. So how about now?
Yeah, you're on slide 2, correct.
Okay. So here is the overview of my presentation today. I'm going to start with some background information and then talk about the control model, which consists of a self-transmission model and also the optimization model we built for the VSL control problem. And then the solution algorithm we developed in order to solve the optimization model. And then the test study we conducted based on a I-5 in Los Angeles area. And then some numerical results I would like to share with you. And then, a summary gonna conclude this presentation. So traffic congestion, as we all know, is a major problem around the world. And from Asia to Europe to North America, from state to state in the United States, and from city to city in any states, regardless of the size of the city, and also from urban to suburban to rural area. Pretty much everywhere we see a congestion, and it's getting worse right now. So active traffic management, ATM, is a scheme that has been used by traffic engineers, planners, as well as decision makers, across the world, to mitigate the congestion, also improve safety on both freeways and arterial. Some examples include, for example, the variable speed limit is one of them. That's the things we are going to talk about, and ramp metering, and also shorter running, as well as the managed lanes. Some examples. So variable speed limit, which is our focus clearly. So some also call it as a dynamic speed limit. So so what happens in the real world is you have a dynamic message board on the roadside, or you have a board, that are hung vertically up in the air with the support from the pole on the roadside. So basically, whatever that might be, you're going to see the variable speed limit, which can be changed dynamically. So what I mean dynamically is that the speed limit can be changed, within the day, any time of day, and based on the real-time traffic and also the weather conditions. So right now, the variable speed limit has been widely implemented around the world. For example, in Europe, Central Europe, like Germany, West Europe, like England, and North Europe, like Sweden. And also in the United States, we have a lot of applications as well. For example, in the state of Washington, state of Virginia, and state of Wyoming. And right now, in city of Seoul, in South Korea, we also have quite some applications already. So generally speaking, we have seen some improved safety, some increased throughput, as well as some reduced emission as well. So the last slides basically focus on the traditional traffic engineering planning, kind of like coming from that perspective. So this slides basically talk about emerging technology. So as we all know, in the past 5 to 10 years, we have a lot of technology that are very disruptive in nature. For example, one representative technology is connected and autonomous vehicle. So 3 years back, when we look at these, we know that ATM is very usable, variable speed limit. And then we look at CFE. So why not integrate the two of them, together and do some research? So that's why 3 years back we conducted research for the U.S. Department of Transportation. So we developed a cell transmission model that can take into account the mixed traffic flow, which means we have human-driven trucks, we assume to be 100%. But for cars, it could run all the way from 0 to 100%, which means it could be 100% human-driven cars, all the way to 100%. All of them are connected autonomous vehicle. So we can take into account the mixed traffic flow. So these slides basically give you a picture trying to illustrate a freeway street with multiple bottlenecks. As we all know, the bottleneck could be caused by multiple factors. For example, the ramp weaving effect. For example, in this picture, we have an on-ramp, closely followed by another off-ramp. So as you can see, this is so close by. We have complicated ramp weaving movements going on here. So clearly, the traffic from the main lane going to be slowed down to some extent. That's why we could have a bottleneck here. Some other scenarios are like this. We have 4 lanes reduced to be 3 lanes. In this case, we have a lane drop. So clearly, we have could have another bottlenecks as well. And a bottleneck can also be caused by, for example, accidents or work zones, or geometrically, we could have sharp horizontal curves or steep vertical curves and things like that. So anyway, due to multiple reasons, we could have multiple bottlenecks. We could experience that on a daily basis. So this example clearly shows that. And then we have horizontally here, as you can see, we have multiple cells. So in traffic modeling theory domain, we're going to decompose the freeway segments into multiple cells. So there are a lot of techniques and models in terms of how to do that. I'm going to skip that. But we just need to keep in mind that cells can be translated to kind of like a spatial dimension, which is roadway segments. And then we assume the fundamental diagram to be triangular relationship between the flow and the density. And when we model the mixed traffic flows, we also convert the heavy vehicles like trucks into passenger car equivalents. Short name is PCE. So PCE itself should be dynamic. The converting process should be dynamic, which means that during different time of day, or also depending upon the type of vehicles as well. For example, the trucks, the PCE could be very large, but the passenger car itself could be 1.0, right? So as you can see one equation here, the PCE itself is a function of a time, which is K, also a function of a vehicle type J. So this PCE is calculated as a gross distance gap of vehicle type J divided by gross distance gap of a car here, as you can see. So if you want to know more, you can refer to this article here, okay? So as we all know, when the demand reaches capacity here, basically these two lines should be discrete in a sense that we have a capacity drop here. So as we all know, in the traffic flow domain, a lot of researchers, particularly in like early on in San Diego State University, like James Banks, Professor James Banks, retired a few years back. He did a lot of research study focusing on the capacity drop. So these phenomena has been verified using the PMS database in California, as you can see here. So our research can account for that capacity drop explicitly. And for a fundamental diagram, we could have one fundamental diagram for different vehicle types. So we're going to have a fundamental diagram for different vehicle types and different bottlenecks. So we are going to combine them into one. So this is just trying to show you one example. So obviously there are a lot of work related to CTM, how to model the traffic flows. So if you're interested, I will have one reference later on. I'm going to share with you, so you're encouraged to read that or to get more information. So to model the connected autonomous vehicle, we use the intelligent driver model, which a lot of people refer that model to be IDM. So IDM was initially developed by Schreiber and others back in 2000. So IDM model can be used and adopted to model the car following maneuvers. So for lane changing, basically in our research 3 years back, we assumed that the connected vehicle just take the default in the vision. So they can change lanes anytime they want. Just take the default. So right now we're developing some lane changing behavior to account for the platooning effect as well. So in the IDM model, as you can see, the acceleration rate of the following vehicle basically is a function of the speed of the subject vehicle, and also the gap distance between the lead vehicle and the following vehicle, as well as the speed difference between the lead vehicle and the following vehicle. So given those three, we can calculate the acceleration rate for the following vehicle directly. So in our research, again, when we model the autonomous vehicle, we basically decrease the headway. For example, when an autonomous vehicle following another autonomous vehicle, then the headway is reduced to be 0.6 seconds. When an AV is following a human-driven vehicle, then the vehicle can be acted as a regular AV, which is 1.1 second. As later on, you will see that in our model calibration for human-driven vehicles, the headways we calibrated it to be 1.6 seconds, which is much larger. So we will have that one slide to share with you based on the case study later on. So these slides, basically, we get to the optimization model we built for the variable speed limit control problem. As you can see here, we basically have two main components. The first one is the total travel time, TTT. So as we all know in transportation, we generally talk about two things and most of the time. One is efficiency. So total travel time somehow can be translated to the operational efficiency. The second component we're talking about here is total speed variation. So as we all know that when speed are harmonized, then more likely than not, we're going to improve the safety. So by incorporating those components into our model, we basically consider two things. We're trying to strike a perfect balance between the operational efficiency and safety. So as you can see, our model is trying to minimize the sum of these two. So we have a W1 and W2 introduced at the weight to reflect maybe the decision maker's preference. And then we actually incorporate another component here. So sometimes we may have multiple variable speed limit control subsystem. If that's the case, then we introduce that as a part of the objective function in order to account for that decision-making process. So as you can see, we have multiple constraints here. The first set of constraints is our decision variable UIK. So U basically means the speed limit that we're trying to optimize. I means a cell, which means again roadway segment, and the K means the time. So we have time and space dimension here. So the variable speed limit should be less than equal to maximum value, greater than equal to minimum value. So the V min, V max, both of them could be user specified value. So by introducing these constraints, we're going to guarantee the safety and the efficiency at the same time. And the second set constraint you can see here is the decision variable belong to a set, and that set is discrete, as you can see here, which means 15, 20, all the way to 70 miles per hour. So in the real world, obviously, when we as a driver on a daily basis, right, we will not feel comfortable when we see speed limit to be, let's say, 17.1 miles per hour or 18.3 miles per hour. So somehow the speed limit got to be integer. That's the first. Second, it better be a multiple of 5 miles per hour. So that's probably preferred by us as the human beings. So that's why I put a set here as an example, 15, 20, 25, all the way to 70 miles per hour. So in this case, as an example, again, the minimum is 15 miles per hour, the maximum is 17 miles per hour. And the last two set of constraints, as you can see here, which basically reflects the change in speeds between two successful time steps in the same cell, and the change in speed between two successive cells at the same time interval. This difference should less than equal to 10. Again, 10 could be set to be 5 miles per hour or 10 miles per hour. I'm just showing you as an example. The speed difference cannot be too large because we as a human being, when we drive anywhere in the city, if the speed limit just changed dramatically from 5 miles per hour suddenly to 50 miles per hour, we will not feel comfortable. And also, this could be very dangerous in terms of safety, right? So this slide talks about optimization. Now, if you look at the optimization model, we know that model is a mixed integer nonlinear model. So in the operation research domain, as we all know, that there are limited amount of algorithms can be used to solve a model like that. It's very complex. It's NP hard in nature. So along that lines, we develop a generic algorithm, which is a meta-heuristic algorithm. We can develop a local optimal solution within a reasonable amount of time. So this is the flow chart I'm sharing with you. Basically, there are two big components. So we are using generic algorithm to optimize the process, optimize the variable speed limit. Then once we determine the speed limit, we use a Visum to simulate, how our driver is going to react to the optimized speed limit. And then we use a CTM to model the traffic flows and make a predictions and provide a feedback between all these blocks. So that's the big picture here. So the case conducted, basically we conducted a case based on I-5 roadway segment located in the Los Angeles area, as you can see here, really close to the downtown Los Angeles. And the starting period basically ranges from 5:30 to 9 a.m. on weekdays. So as you can see here, we have 3.5 hours. So basically, we use the first 30 minutes as a warm-up period in the simulation. And then we use the left, which is 3 hours, actually used in our modeling work. And then the field data are aggregated into 5 minutes counts. And the length here is about 5 miles. And in the PEMS database, we also have truck percentage calculated as the entire traffic flows here. As you can see, different truck percentages over time. So these slides basically talk about bottleneck. So in the past, we conduct a research study for North Carolina Department of Transportation. So we have some work basically allow us to identify the presence of bottlenecks based on the speed data, probe vehicle data, basically is rights, earnings in the past. So for example, we use the travel time reliability measures. One of them is the frequency of congestions. When the speed drops below a certain percentage of the free flow speed, for example, 60% of the free flow speed or 75% of the free flow speed, then we can declare that the traffic is congested. Then we say, hey, there could be a bottleneck here. And particularly when that phenomena happens very frequently during the day, then we're gonna have methodology in place to identify those bottlenecks. So having said that, as you can see one picture here, vertically we have 36 intervals. We have 3 hours. We have 5 minutes as the interval. 3 hours we have 36 intervals. We also have speed data. For example, the yellow color here is 60 miles per hour. The dark blue here is 10 miles per hour. So visually, by just examining the picture graphically, you can see that clearly that we might have 1, 4, 5, 7, 9, and 14 as a bottleneck. So particularly when you see the 4 and 5, they're really close by. Particularly we're driving in that direction. 4 is upstream and 5 is downstream. So 4 and 5, because they're so close by, we integrate them into one, combine them into one bottleneck group. Because when 5 is congested, chances are the queues could be built up, upstream of that point, right? So that's why 4 could be a bottleneck naturally. So that's why we combine 4 and 5 into one, as one bottleneck located at this location 5. And then we have we make assumption about this. We have 3 variable speed limit subsystem control system here, and then we have the location of the bottleneck here, highlighted in red here, and we have models here invisible. We have root detectors. We can collect the speed and the flow data. So the numerical results here. So we modeled 3 types of vehicles. Obviously, the trucks is 100% human driven. We assume to be that way. We can always relax the assumption, no problem at all. But back to the time we conduct the research, we assume that way, 100% human driven truck. And then for cars, it could be 100% human driven all the way to 0% 100 human driven, and then 100% connected autonomous vehicles. And then based on the PMS database, basically for that particular roadway segment, that mile stretch, we fitted the data. We used that method developed by Derby Sogolu back in 2008. It's very famous. And then we identified the capacity at different bottlenecks. Drop capacity, as you can see, the capacity drop is very common. It ranges from somewhere from 4% all the way to 15%. That's verified by multiple researchers in our domain. And then we have cars, basically have a free flow speed. We assume that for trucks, the free flow speed is 5 miles per hour less than the cars. So as you can see here, cars -5, you get a free flow speed for trucks. And then based on the PCEs, we calculate the critical density and that. So this has nothing to do with modeling, but it basically based on the PMS data, we did some data pre-processing. We get all this data, okay, based on our case study again. And then as we all know, in transportation field, particularly for PMS database, we got a real world data, it's coming from the real world. They're ground truth data. On the other hand, we have simulations coming from the software vision. So we always need to conduct model calibrations. For example, vision, there are several model parameters involved inherent in that software. So we must conduct calibration so that the data simulated coming from the simulation is really, really close to the real world data, so that we have a certain level of confidence that, for when we conduct simulation, our results we're going to be getting out of a simulation will be very confident that they're really high quality, right? You can trust in those results. So that's the point. So couple of the parameters just to show you as an example. For example, CC0, CC1 in vision. CC0 is a standstill distance. Headway time is CC1, headway. So based on the PM's database, we conduct a model calibration based on some of the model we developed in this paper. So we calibrate headway to be 1.6 seconds for human-driven vehicles. That's right now in the real world in the PEMS data, which is true, right? 100% human-driven vehicles. And then we also calibrated the maximum acceleration rate, maximum deceleration rate in normal conditions, and also the S0, which means the front bumper to end bumper of the leading vehicle, front bumper of the following vehicle. So the gap between these two. So for human-driven vehicle, we have a 4.13 feet. For AV, when an autonomous vehicle follow a human-driven vehicle, we assume that gap could be 0 because we trust the technology. Certainly, this parameter can be changed anytime, right? And also that when AV follow another AV, then it's connected. We assume it to be that way, and then we have 0 as well. In terms of headway, as we discussed earlier already, so when autonomous vehicle follows another autonomous vehicle, then we assume it to be 0.6 seconds. Again, these parameters have been well calibrated by a group of researchers from UC Berkeley PASS program. Sheila Dover is one of them. Is leading researchers, around the world. There are multiple papers you can, if you're interested, you're more than welcome to read. So this is how we get the parameters from those studies. So next slide, as you can see, we have 3.5 hours in our model VISM. So we have first 30 minutes, we use that to warm up for our simulation. And then the left 3 hours from 6 to 9 for our simulation. And then basically prediction horizon is 5 minutes. We're gonna change the speed limits every minute. Discrete time steps means 10 seconds. So what it means is this. Okay, what do I mean that all these 3 parameters is this? So we're going to make a decision, update the speed limits every minute. But we're going to make a prediction into the 5 minutes into the future. In other words, we have 5 time steps ahead. Because we want to make our model and also the prediction really reliable into the future. Because you cannot make a decision based on the myopic short-term decision. So we look at 5 steps ahead. We make predictions. Based on those predictions, we are going to anticipate how drivers react to different variable speed limit we're going to optimize. We have that capability to do that. And then we are going to optimize and display the speed limit. And then the driver going to react to the updated speed limit. They make changes. And then that's kind of like a rolling horizon. We make a decision on a rolling horizon basis. And then we use W1 equal to 0.9, which 0.9 times total travel time, which means that we give more weights on the efficiency versus safety. Safety, we have 0.1 basically as the weight. Now we design 5 scenarios in this presentation, but in our papers, actually, we have 7 scenarios. But in this case, 5 scenarios I want to share with you. Scenario 1, 100% human-driven vehicle with no control at all. Scenario 2, we have 10% autonomous vehicle without a control. Scenario 3, 100% human-driven with control, CDM without considering mixed traffic flow. Scenario 4, we have 100% human-driven with control, extended CDM. And scenario 5, we have 10% AV with VSI control and extended CDM. So this table basically present some of the work as the research funding we got back then. So for example, scenario 1, which means all human-driven vehicle without a control. So we're going to use that as our base for comparison to show that in other scenarios, we're going to improve the results. Total travel time, we use that. Average delay, average number of stops, and also emissions. As you can see here, scenario 1 is the highest, pretty much across all categories. Scenario 2, which means still 10% AV, but no control. So we got some improvement compared to the baseline. And then 3 and 4, all human-driven vehicles with control. So this will be improved significantly. Later on, we have some even 10% autonomous vehicle with VSL control. Then this one clearly is the best across all categories. So this slide basically show you the speed harmonization impact of VSL control. So this picture shows the speed control map. Okay, so we have 2 dimensions again here. The x-axis corresponding to the cells. Again, That's a space dimension. Y-axis is the time. So we have a time domain, it's time and space. So if you draw two lines here, horizontally and vertically. So horizontally, we have a time. We fix the time interval at that time instant, one t equal to 140. And then we can see the speed transition between cells. As you can see, color-wise, we see gradual change, which indicate a smoother transition of speed, among roadway segments. And vertically, we kind of like a cross section. We stand there, we look at that, and then over time, we also have speed harmonization. That phenomena being achieved as well. You can see that. So these slides basically show the time instant, same time, the speed change between cells. So these slides basically shows that at the end of the simulation, the vehicle speed at the most congested bottleneck begin to recover at the end of the simulation clearly. And then finally, this slide basically shows scenario 1, 4, and 5. As we all know, scenario 1 means the real world, all human-driven vehicles and no control. As you can see here, we have a capacity drop clearly. We get to this, we have a drop capacity and zigzag here. But 4 and 5 basically, 4 is all human-driven vehicle. 5 is 10% AV with control. You can see that both with control, we have a steady and higher discharge value, like this, much higher than the 100% human-driven vehicle without control. Clearly, in both, at both bottlenecks 2 and 3. So this slide basically summarizes what we did. We integrated VSL with CAV. We developed the extended cell transmission model, which can consider both the capacity drop and also mixed traffic flows. We conducted the testing of our model using the real-world freeway corridor in I-5 Los Angeles area. And then the results shows that we have enhanced efficiency, improved safety, and reduced emission. And finally, we have some other results show basically CACC, and you can see more results in our paper. But due to time constraint, I'm not going to talk about it in our slides. So these slides basically give you some idea what we did in the past. As you can see here, this presentation basically the results mainly adopted from the first paper in this block, which we published back in April 2019. Optimal variable speed limit control in CAV environment for relieving freeway congestion. And then the second block, we have 2 papers along the lines. As you can see, we have bottleneck, variable speed limit control at bottlenecks using geometric algorithm topple search. And then the third block, as you can see here, these basically deal with how to conduct the model calibrations using the real world data. For example, the PEMS database. And then the last 2, basically, the results are based on the research study we conducted for NCDOT. So we use the vehicle probe data coming from NRIX, right now, riders, to use those travel time reliability measures to identify bottlenecks, and how to improve the bottleneck, how to rank the bottleneck, how to develop countermeasures to improve the bottleneck, and cost benefit analysis and things like that. We have some report based on all these. Okay, if you're interested, you're encouraged to Google and find the paper. Also look at the research report we published. So with that, thank you all. If you have any questions, I'll be glad to answer.
Great. Thank you so much, Dr. Fan, for today's talk. So, any question to Dr. Fan? Okay, while others are warming up, I have one question. If you can go to the slide that you had your optimization formulated, the cost function that you had there. Forgot the slide number.
Yeah, this is the one.
Yep. So as far as the constraints, we can see the last two UIK plus 1 minus UIK to be less than 10. That is about the comfort, and presumably the last one is about the safety. So not sure if is a good idea to consider safety with respect to relative velocity. Let's say if the two vehicles are a large distance, if there is a large distance between the two vehicles, then why should they maintain a relatively low relative speed? So can you comment on that, please?
Sorry, Ali, I just lost you. I did not hear your question clearly. Can you repeat that again, please?
Okay. My understanding is that the last constraint here, maybe I think there is an echo from your side. Yep. So the last constraint over there seems to be for safety, right? And I was not sure if it is right approach to consider safety in terms of relative speed, because it's if let's say the relative distance between the two vehicles is relatively large, then why should they have a relatively low speed? So can you comment on that?
Okay, yeah, that's a great question, Ali, and I ask your question. So actually, the last two set of constraints, those correspond to the safety. Because the third one we're talking about, the speed difference on the same cell between two successive intervals. And the last one basically corresponds to the same time interval, but two different roadway segments. They're next to each other. So to answer your question, so as we all know, the safety could be compromised due to two reasons. One is the speed is too high. Like you mentioned, the speed is, the absolute speed is too high. The other one, which is our focus, basically talk about the variable speed limit, which means the speed harmonization. We're trying to harmonize the speeds between vehicles. So we as a driver, we interact, we share the road with other drivers, with other vehicles. So we're trying to minimize the speed change, speed difference between the lead and the following vehicle, so that we may not get into the rear end accidents.
Okay, and that's with the assumption that they are relatively close, right? Okay.
Yeah. Because we talk about bottleneck, basically highly congested more often than not. So that's why we're trying to harmonize the speed. So the speed difference is not that large. So kind of like sort of like a coordination to some extent.
I see. Okay. Thank you.
Thank you.
Okay, great presentation. I enjoyed it very much. Thank you so much. Okay, my question is, is, okay, the bottlenecks, as you mentioned, basically those that are considered you are entering or exiting a given highway. But I thought that these are all taken into the consideration during the construction of the highway. That is one, but especially those that you mentioned, I understand about the bottleneck, but the bottleneck that are responsible or due to minimum allowable distance for entering and exiting from the same highway. That to me is the flaw. The first flaw is in the design. They should have a minimum distance between exit and entrance, basically. Okay, and then which I am going to assume that they have already taken this into account. Then the question that I have from you is this: despite of this, that because in my mind you are making an extreme case to justify what you are trying to justify. You are telling me that the distance between the entrance and the exits are not good enough. I think that is what I get from you, right?
Yeah. Yeah. Thank you for your great questions. So to answer your question is this. Okay. So in transportation, we typically have a cycle. Infrastructure-wise, we have planning, design, construct, operate, and maintenance. So we have 5 stages. You basically refer to planning and design stage. So in terms of the space between on-ramps and off-ramps. So that obviously our research basically take this as given. We assume planning is done, design is done. Now we're getting to the operation stage. Given what we have, given the roadway design the way they are, how we are going to manage the traffic in order to improve the safety. So that's the first part to answer your question. The second one, you talk about the work zones. Basically, our model will work for bottlenecks caused by anything. Basically, it could be in our case, could be close by ramps, which is weaving sections, or lane drops, or shorter-term work zone activities, or long-term lane drop, or things like that. So our model is kind of like a general, different cases. We can change our model with some minor modifications. And still works.
Yeah. Okay. All right. Thank you.
Thank you.
Joe, you're gonna asking that question, or should I read it?
Is that coming from chat? Okay, Joe asked a good question.
Yeah. Okay. The question is that did you feel that human drivers all obey the VSL exactly? If so, is it a realistic assumption? And does it impact does this assumption affect the results?
Okay. Thank you, Joe, for your question and for your time as attending my presentation here. So to answer your question, in our simulation model, we assume the connected autonomous vehicle to follow the speed limit. But for human beings, human driving vehicles, we actually, the speed they're driven could deviate from the optimized variable speed limit, which means the driver may follow or may not follow the speed limit. So in our simulation, typically we have different parameters. Speed could go up, go down to some extent. So yeah, we do did not assume that the human driver will obey the VSL exactly. And there are some stochasticity associated with the speed, given the speed limits. Thank you.
There was another question that was posted there before we wrap it up. I wanted to know the design of control model from slide 6. Can you please explain? So there is a question on slide number 6.
Number 6, okay. So this we use the fundamental diagram to model the traffic flow from a macroscopic perspective. So typically we assume the fundamental diagram to be, triangular shape, parabolic, those different forms. So in our case, we assume to be triangular relationship. And then we did consider a capacity drop here. So as you can see, the line here, we have dashed line connect these two. And then we have a different vehicle types. We have different fundamental diagrams. For example, we could have cars and trucks. And then we have, ways to combine these two into one. And there's quite some derivations going on behind the scene. So if you're talking about the fundamental diagram, then that's the way I answer your question. But if you're asking these, then there are a lot of derivation involved. So I would encourage you to go look at our papers. Our paper also refer to bunch of papers. Obviously we did not derive this equation ourselves. We also adopt quite some work from other researchers as well. So did I answer your question? I think,
Thank you. So any other question before we wrap up today?
I had just one quick question.
Yeah, go ahead.
Yeah, thanks, Dr. Fan. I think I was curious about, did you develop the VSL control to be implemented in real time? Or do you expect that this would be something that is pre-calibrated and will be sort of applied as you, like from day to day?
Oh, thanks for your question. So right now, we're still at the research stage. We hope that with the development of technology, right, in computer power, in memory and all that, also hardware in terms of communication, then hopefully the software, which is VISM, can be connected to the, maybe can be incorporated as a part of the decision-making process. So for now, this is still in the research R&D development stage. It's not ready for implementation yet, because as we all know, CFE itself is a process still evolving quickly, probably in the next several years, right? So I guess the point is that 3 years back, we look at this, we look at the VSL, we look at CFE, and then we saw a gap. So our thought is, why not integrate these two and do something? That was the purpose. And obviously, even during the past 3 years, there are a lot of things still evolving, a lot of research going on, right? There could be, we all make some contributions. Hopefully, in the near future, we make these hopefully one day going to be ready for implementation. Yeah.
Thank you.
Thank you.
Thank you. So with that, it is now almost 4 p.m. With that, thank you so much, Dr. Fan, again, and wish everybody a great weekend.
Thank you all. Yeah.
Thank you. Bye-bye.
Yeah.